Okay, let's get started again so we can finish on time. Can you hear me? It's okay? Back here. Okay, we finished this short overview over optimization algorithms. I'm erasing everything. Okay, so this was a bit the picture. There were like 4 cases, and all these 4 cases, they are in the lab. So really make sure that you get the lab in terms of the math, how to compute the gradient or subgradient, and also in terms of the Python code to really experience how do these algorithms jump around in the space of the W's. Okay, so that's all about optimization when the W can be anything, when it's not anyway constrained. So W can range over the whole space. There is one small different case is that sometimes we might have constraints on the W vector. Sometimes our weights have some special meaning, or so maybe they have to be in some particular region. Maybe you have a machine learning model where you want your weights to be non-negative or in a box or in some special set. So that can happen quite naturally. And this is the picture for that. So it's really the same thing as we had before. We want to minimize the function, but now there's this additional thing, so that not over all W's, but only those W's which are in particular set, which you call C here, and that C is a subset of what we had before, right? Before we had D variables, and now we only have a subset of this. Sorry. So W is in that space, and C is a subset of that. It could be the whole thing, but in general, it's a subset. Okay, the picture on the left is what we had before when we thought about gradients, right? Again, so on the bottom you have the 2 variables, say 0 and 1 if you want, and vertically you have the objective function L. And then again, I actually recommend the picture on the right more, because it's easier to see, right, in just these 2 dimensions, right? So this is the space where the parameters live, and here you can see again these are the so-called level sets of the L function. So here it's small, and then here L is a bit bigger. So these lines here are the lines where the function value is constant, it's the same. So it's going up when we go further out here, and when it's the darker region means that the value is lower. So we are more close to the minimal point, which is here in the middle, right? Yeah, that's very simple. So that's just a definition of a constrained optimization problem as compared to what we had before. Now, yeah, what this constraint set C actually is, that depends a lot on the application. But we want to think of how can we now optimize this with gradient descent. So before we get there, we should again revise convexity. We said we already know what are convex functions, and I think most of you also know what a convex set is, because now we're talking about the set C. We want to ask when is it nice, when it is easy, and which set C's are a bit more complicated. So okay, this set here, is it convex? Who would say that this is the case? Raise your hand. Yeah, that's a good ratio. Who would say it's a non-convex set? So who is unsure? So it actually is a convex set, because for any pair of 2 points, it happens to be that the line segment between them is also part of the set. And that is the definition of a convex set. So yes, it is convex. This one here, it's already showing you kind of the counter example, because yeah, for these 2 points, the line is not in the set, right? So this is not convex. So, and what about this one here, the last one? Who is saying that this is convex? Who thinks it's not convex? That's a bit more of you, and you're actually right because you can't see it nicely on the beamer maybe. But this means that the boundary only belongs to the set, like these parts, right? The part here is not part of the set. So this is showing that it's not a convex set. But this set, the boundary is there, and sometimes it's not there. It's just a set, but it's not a convex set because this is the counterexample. Okay, why do we care about convex sets? It's actually, they make life much easier to do the optimization. In a similar way as we've seen that convex functions make it easier to minimize them, right? We saw that those had only a unique minimum. There was not any local minima. That was nice. There is similar benefits you can get when you have convex set and want to constrain your optimization to these. So one nice property is also that intersection of convex sets are. It's actually hard to draw a non-trivial convex set. Okay, here's a convex set and 2 of them. Here's their intersection, and so it happens that the intersection is also convex. That's nice. So this is really easy to prove when you use the definition here. So I encourage you to try to prove this because it's not completely trivial, because you see if you take the union, for example, then that's not the case. If I would take the union of these 2 sets, then here is a counterexample. So the union is not maintaining this property. But the intersections are fine. Another property is about the closest point in the set. So that's what we call a projection. So given that you are somewhere, you can ask what's the closest point in the set to my current position. So that we have here, you are somewhere, here is a point, W prime, and you ask, let's say in this set here, what's my closest point? And that's what we call a projection. So that's the point which we have here. The point in the set which is closest in the distance, in this norm. The nice thing about this, if the set is convex, is that there is only one such point. It's not that this one, there is another one which is also closest, right? There's just one closest point. Why is this of interest? It's actually because what's going to come next, if we want to optimize and do gradient descent in such a scenario where we have to stay inside the set. So there's going to be a trick which we want to apply to make it work, right? So here is gradient descent, but we want to stay inside the blue region. So how can we do that? Let's do this step by step. So we are currently here at the point W, and we want to perform the step that we all used to. So we want to go some step size times the negative gradient. We want to go here. Okay, that's what we all used to do. That's going to be happen from time t to time t plus 1. But then, we can't do that because that point is not in the set. So we are in trouble. We cannot, it's not legal, right? We only want to optimize over points in the set. So we need to stay in it. So we want to minimize only over the W's in the set C. That's our task, and this is clearly not doing this job. But so what we do is, after we've gone there, we we do the projection, we need to go back to the set somehow, and doing what I just said before, the closest point in the set, maybe that's a natural thing to do, right? Okay, I'm out. I'd like to go here because here the function value is much better, right? That's what the gradient tells us, but I'm not allowed to go there. So I just go to the closest point to where I'd wish to go, which is the point here, the projection of this point of wishful thinking, which I would have liked to go here. So this point here is the classical gradient step. That's where we would like to do, but we are not allowed. What I do, I just try to do it, and then I apply the projection, which is the closest point in the set, right? And yeah, because if the set is happening to be convex, then we know that this thing is actually well defined. It's always going to be just one point, so it makes sense to go there. Yeah, that's all. Here's the definition of the projection again. The only question that comes up is how expensive is it, right? So the gradient steps, they were nice, not too expensive, but now this additional projection could make life much harder for us. It might be very costly. If the set has a very difficult shape, then this can cost a lot of time. And so that's an issue. And that's what we also have here. So you need to think a bit about the computational cost. So in machine learning, the nice thing is that the sets are usually not so complicated. Maybe in many cases we're going to discuss this later again, that you will maybe use a Euclidean ball as your constraints for your weights, that they don't grow too large. So why would you do this? This is coming later, but this concept is called regularization. You want not to search about all the models, because that might make you overfit, which is actually going to be discussed next week. But you want to only search about the simple models, because the simple models, they are nice, so they allow you to make better predictions on new data. So that's the topic of next week, actually. And like constraining your weights onto a simple set, that helps you a bit. That's one way to say, I only care about the simple models. So you can say, I only want to optimize over set C, being maybe the Euclidean ball here in D dimensions for your points W, right? That's one way to do it. There are other ways to do. So yeah, for this round standard ball, it's very easy to project on it, right? You will just, if you happen to be outside, you could just scale back to here, and then you will be in the region again, and things are fine. That's a very cheap computation. There are some other shapes which are actually used, or you could think if it's a box, then it's also not too hard. And just to give two examples. But yeah, don't forget about the computational cost. But the nice thing is, if gradient descent works, which is the case, for example, for convex functions, then also projected gradient descent will also work on the same function to optimize over any convex constraint set, which we now additionally have in our problem. So then it turns out this variant here, which is a modification, that one will have the same convergence rate. So let me actually, yeah, this is maybe, so it's maybe a point to clarify again. I got this question about convergence, right? So how do we define convergence? What do we do care about here? So what we want is convergence to an optimal solution, right? So and let's just maybe formalize it. It's a good it's a good exercise to think on this optimization topic. So what does it mean to converge to an optimal solution? I'm not writing the optimal solution, but just one of them. There might be several, right? So what does that mean? So, I mean, if you had analysis algebra, then you've probably seen conversions of sequences, right? Which is just you look at the sequence of numbers, and at some point they happen to stay the same, right? But here it's slightly different. So here, convergence to an optimum is meant in a very simple way, right? We look at the function, how fast it goes down, right? So we are currently at some point t. So this depends how many steps we do. After t steps, I'm at this point w, and I got this function value. This is my cost. And what I want is that this is going down as quickly as possible, right? It should go down to the lowest possible value. The lowest possible value is the value here at some optimal solution. That's what we said when we defined the optima, right? W star is at some point where the minimum is actually attained, right? So that's what W star is. And now we look at how far are we away, like how is our cost different from that? And that's what we mean by convergence. So this is always bigger than 0, right? Because nothing can be better than this. But what we want is that this goes down to 0 quickly. So for example, it's smaller than some number divided by t. That would be a very nice convergence. For example, you do t iterations, and what happens is that your error goes down with the t increasing, right? That's what we mean by convergence. And then there is the whole theory you can do is you can ask the algorithms we have seen so far, how fast do they converge, right? So one thing again is very important, that there might not only be one optimal solution, there might be several, but the optimum value, there is only one such value. And so that's our measure. That's what we'll always do in machine learning, to measure the cost of the current parameters you have, right? How good is your model trained? It's given by the current cost on the training set. And then we will see next week that you can also look at the cost on a test set. But this is the measure, and this is what it mathematically means that you have an optimization which converges to the optimum. Does that make sense? So, yeah.
Is there a better method for solving the constraint optimization problem than projected LGD? Or is it the best?
So yeah, what's the best rate? So unfortunately we don't have, in this course we cannot discuss the rates in detail. So this something over t, that's one possible rate. And you also ask about, yeah, now I'm constrained, do I have the same rates? The answer is yes. Like all the rates which you have for all these 4 cases here, they're something we are not going to prove a theorem. But these rates, so how fast the error goes down, they also hold when you have a constraint set. When you do what I just described, so when you after each step go back to the set, then the rates are still fine, but only if the cost is convex, yeah. And then what's the best possible rates that you can possibly achieve? That's then a more advanced topic on advanced optimization. Yeah. Okay, this is for constraint optimization. That's actually what I suggest you to do. That's one way to deal with constraints, right? There is actually a second way, which is to try to take your constraint problem but go back to what we had before, right? Could you somehow transform it into an unconstrained problem? That would also make your life easier, because then you don't have to worry about these projections anymore. So this is really a second type of thing you can do. And let me give you an example. so here is the constraint problem again, which we had. So, okay. That's what we try to solve, right? But we want to remove this constraint set C. And one way to do it is to kind of transform it into an unconstrained problem, right? The problem here is not constrained. That's nice. So, sorry, this is a problem unconstrained, which is what we discussed before, which was much nicer to optimize, right? So can we take this constraint C and turn it into an unconstrained one? And that's what's actually happening here. I had my original L, that's always there, but now I'm trying to add another term to my cost function, which hopefully has a similar effect. So this additional term should punish when you're outside, and it should be no influence when you're actually inside the set, because then you care about L. But when you're outside, you want to punish the method that give it a very high cost to bring it back inside. So that's the idea of here when we try to turn a constraint problem into an unconstrained one. Yes, and so this is the concept, of course, makes sense. But now let's see more concretely. Now, how would I define such a penalty, as we call it? And the easiest one is actually this one here. It's just a brick wall, whatever. The function is actually infinity when you're outside. So you have to pay infinitely much, like this here, when you leave the set. So that's what that means is you're just not allowed anyway. You will never be allowed to be outside of that. So it's a bit a difficult function to optimize because that indicator function, as we call it. So maybe if your set C lives here just in one dimension, here is C, then this function is a bit nasty. It's like infinitely high, which I cannot draw, right? Plus infinity, and then it's 0 when you're actually inside. So this is a function which is not continuous. So it's pretty bad. To optimize that, again, it's not going to have gradients here at the boundary. It's not differentiable. So we cannot optimize it so easily. So this is more a conceptual trick, but in practice, it's very hard to deal with that. So actually, it's not giving you a new method. It's just reformulating the problem. But this is helping us because we exactly want this concept. But now let's try to be a bit more realistic and have another kind of penalty, which we have here. Sorry. So this is when we just define a function which measures, again, how far are we outside. And there are simple things to measure that. You can actually define your own measures for that. So whatever the set is, you can define how you're going to measure your distance to it. A very natural way is this one here, which is the distance if your set is a linear constraint set. So this is just a linear equation. Sometimes in life applications there might be a linear constraint which needs to be satisfied. So then the W must always, I don't know, maybe all these entries must add up to 1. Then that's a constraint. If that is our constraint, then we can measure how far actually are we away from that constraint by just looking at this number here. So AW minus B, that's actually a number. So let's take the easy case when A is just one row vector. So then this thing here is one constraint. Then B is a number. And then what you have is AW minus B, that's a number, right? And you can look at its absolute value. If you satisfy the constraint, it's 0, it's nice. If you don't, it's measuring how far you're away. It's actually the same thing as we used in mean squared error for if you're interested. So this is one thing you can do, and what I described now was only for one linear constraint, but A can also have more than one row. Then you actually can still do this. Maybe I have 5 linear constraints. That means that there are 5 rows in my A matrix. And then the B also has 5 numbers. So each of these 5 constraints needs to be satisfied. And how much it's actually satisfied, that I'm measuring in this way. And also maybe I have a trade-off parameter. That's also something which is coming back a lot in the next week. So when we have 2 goals, maybe the first one is how good my model predicts, so how my model fits, and maybe the second term is maybe how simple is my model. That's something we have very often. And then there is often a trade-off between the 2 goals. Do I fit my data very well, which is just make this small? Or do I want my model to be simple, which you more say that I want this thing to be very small? So this just conceptually that this is kind of natural to have 2 parts in your objective function. And here is also that this is what we call a relaxation. We wanted this to be exactly satisfied, but we said, okay, we take it a bit more relaxed. This is actually why it's called a relaxation, so that we just measure quantitatively how far is it away from the constraint. And there is a whole other theory which is called the theory of Lagrange multipliers, and that's also something alternative you can do. And it's in the same setting as we had before. When you have these linear constraints, then there is a trick you can do. Instead of adding this norm, which is just a non-negative measure of how far you're away, instead of that, you also add new optimization variables. You introduce a new variable vector. There's one new variable for each constraint. So yeah, to clarify how many of these variables are there, we should give it a name. That's the number of constraints you have. Maybe you have m constraints. That's the number of rows we had in this A matrix, which is called the constraint matrix. So if the A matrix has m rows, then that's the number of additional variables are now introduced. So m rows, and how many columns does A have? Anyone? D. Yeah. Thanks. It's getting late. Yeah. Okay, this is just among these other concepts. How can we solve constraint problems? This is a trick you can apply. But say if you want to go for the simpler method, then maybe if you can do this projection, then maybe do that. If it's more difficult if it's unclear how you would get to the closest point in the set, then maybe it's better to do something like that, to just add a penalization term of how far it's off from what it should be. Is there any question or comment? Yeah. Yeah, do the sets have to be convex? You can still apply the method anyway. That's the short answer. So people do this even when the sets are not always convex. But then it's a bit risky. So if the set is not convex, then you don't have the theory. Then you don't have convergence as we defined it here. So then conversions will be unclear. Maybe in practice you might be lucky, it might still work. But the theory we have will only work when the Z is convex, and additionally also the L, the function, must also be convex. Then we know how quickly it decreases. But in practice what people do is they just apply the same algorithm anyway, and they use gradient descent anyway, even when there's no convergence guarantee necessarily. That actually brings us to this one. Maybe you can do this now. So which is, why I didn't tell you so much about why do we do convex, why do we do non-convex. So this is a bit the picture in real life, right? So all the important applications we care about, they are actually non-convex. So we don't have this nice property, which is a big problem, right? And why is it a problem? Because of these points here, the fact that they have many local minima, possibly. So if this is my function, right? If the picture looks like that, that's again I have two parameters and one number. Then I could be in trouble because the gradient steps, which are here, they might get stuck, right? The method might converge to this thing here, which is not the true solution. The true one would actually be here. So that's something that could happen, and which actually also does happen in reality. But nevertheless, we have to work with the methods we learned. And the nice thing is that all the methods we have seen now so far, they all still work very nicely in this setting, right? We don't have the theory, but it's the best methods we have, right? And at least we know that those methods, they are safe if the problem would be nice and convex. Then so this gives us some. So first of all, it gives us some security that this is a reasonable method, and also it gives us the strong proofs, right? We know that this thing would work perfectly if the problem is convex, which is the one that you actually solved so far in the lab this week. The linear regression with these two cost functions, they are actually convex, so it's nice, and we do have the guarantees. The nice thing about, so that might be a bit troubling, right? So do we just lose all the theory? That's, on one hand, that's a bit the case, yes. But on the other hand, what you also have is that all these insights we gained from the convex world, like we saw that, gradient descent was, the stochastic one was much, much faster than the other one, and we had these proofs about convergence, which gives us insights. So all these insights, they very often still translate to the non-convex world, right? It's still going to be the case that stochastic gradient is much more efficient than batch gradient. So, and many other observations about these algorithms, we develop them on convex problems, and then we apply the same algorithm here in this scenario. And yeah, if you're lucky, then it does not happen that we're stuck in the local minima. And sometimes it still happens, but that's the status we currently have with neural networks, right? There is no proof that this thing will go to the right one here. It might go to this one here. But yeah, still the insights, they help us. And so here you would have the global minima. Yeah, that's a bit unfortunate, and that's also a very important research direction at the moment, right? That maybe there are some easy neural networks for which we could still prove something, that we could prove that we can train them, or so that maybe gradient descent would work, right? But this is only starting that some results like that are coming up. So most of the results are just the ones I showed you for convex. Okay, we are almost done. I have 2 more slides, or 3, about the concrete implementation of these methods. So how do you do it in practice? So one thing we already discussed a little bit is the step size. How should I choose it? So that's what we have at the bottom here. Step size can be very small, then you almost stay where you are, but the advantage of it, small step size has the advantage that it's actually safe. So it doesn't have it will not have this property that it will jump away from the optimum and jump like crazy, go further and further away, which we had seen actually in the one-dimensional example here, right? So yeah, it has been a while. Yeah, here in this 1D example, we said when the step size is bigger than 2, very bad things happen, right? We were actually here, started, then if it's bigger than 2, then you jump here. Next step, you will go here, then you will go even further. So that's what's going to happen, right? It's going to diverge and completely useless. So this is an instability of the gradient descent. And that really happens in practice all the time. So especially when your model is not such an easy function, then this is going to happen. And so if you observe it, then maybe the cost will get up instead of down. Then you should probably work with a smaller step size instead. Because if it's small, then we know in a small region the gradient will bring us down. That's by definition. But in the long term, over a longer distance, we're not sure, right? That's why the instability can happen. So small makes you safe, but it's also slowing down the whole process because you only step very little. You almost stay where you are. So this is the trade-off, right? Too small, slow conversions, but safe, and too large, just going to diverge. So, yeah. Any comments on that question? For convex problems, there is some theory how we can set this to be safe, but it's not available for all the non-convex problems. Okay, then how long do you run it? That's also that somebody asked this on Tuesday. The short answer is you would just run it as long as your budget is fine, or that you see that it doesn't change the function value much anymore. So this is a bit of a problem. If we have a non-convex function, then we're never sure if this method actually converged already, or if it's still going to move, or if we're even close to the optimum or not. We don't know. If the problem is convex, then it's a bit easier to see when to stop, because we will have some information that the optimum is not so far when we look at the gradient here. The gradient is defining this supporting plane, and very often people actually look at the norm of this gradient of the cost function, and if that gradient norm is kind of small, so maybe you take the norm of it, if that goes very small, then you know the landscape is very flat. It's not going down much anymore. So then maybe that's also a point where you can stop. But it might not always be a good measure, because in the non-convex case, this does not tell you anything about the actual true optimum. So this is only a practical trick. This is not theoretically valid for general problems. It is actually, there is some theory, if the problem is convex, then this is a reasonable quantity to look at. Yeah. So when this gradient becomes small. What about the stochastic gradients? So you could look at these as well. So in my step, I use the ends one of them randomly. Could I look at this and see if they are getting small? Are they going to 0? when we converge. So that's actually not the case. So yeah, don't look at the stochastic gradients. That you can think about this when you think about a simple sum. It might be that the gradient of the sum is 0. That doesn't mean that the gradient of the individual ones is also 0. That's not necessarily the case, right? So some people still do this in practice when you train a neural network, but it's actually not so justified. But it is maybe a good idea to look at the gradient of the whole function to see when could be a good point to stop, or just run it as long as you can. So yeah, then there is for one of the cases we've seen when there's just no constraint, then there is a nice necessary condition. Then and this we're actually going to use a lot in practice, and also in some of the future exercises. So there is a necessary condition for being optimal. So when some point W star, what's something that needs to be satisfied, that if it's optimal? So if it's optimal, then one thing for sure will be that the gradient at W star must be 0. So it's the 0 vector. And this is only the case. It doesn't work for constraints, but that works for the earlier case we discussed. So okay. So if it's 0, it doesn't. So if it's 0, it doesn't mean that it's strictly optimal. But yeah, if it's optimal, then for sure this is going to be 0, because you see it here. That's a point which had 0 gradient, and yeah, if it's convex, then it's actually already giving you a much more useful information. But again, it's not sufficient. So. And yeah, if you want to read a bit more on this, we have in the appendix there is also a sufficient condition that you can check, and that sufficient condition is checking a bit if the situation looks like this or like that. So here gradient is 0. Here it's also 0. So for this is convex. So that looks fine, right? But this is concave. You see that the left one is not a minimum, but the right one is a minimum. That has to do with this second condition, which is exactly about that. Is it curved upwards from where I am, or is it curved downwards from where I am? And that's not strictly required from you, but if you're interested, you can see this in the appendix of these notes. Yeah. Okay. And again here, if you want to read, if you don't know this big O notation, then that's a good point to read up on it. And yeah, the most important thing I would say is that you really look at the lab of this week and make sure you get this right in these examples. Yeah. And next week we will have Rüdiger Robanke starting to explain overfitting and generalization. So